Welcome again to Let's Talk Chemistry with Pastor Dan. We're going to look at nuclear fission and nuclear fusion, the process for each of these. Definition of nuclear fission, and if I'm going too fast, just pause the video. Energy from the splitting of atoms. So splitting of atoms is what we're looking for. All right. And the process we have right here for nuclear fission. The process, we refer to this as a chain reaction. Definition of chain reaction is where one reaction results in future further reactions. So one causes the breakdown of the next one, causes the breakdown of the next one. Now, this was first identified by the Italian Enrico Fermi, and this went on for quite a few years until a group of scientists named Miner, Hahn, and Stossman. There was another woman that's all in there. I forget her name right offhand, but there are four of them, and they created enough of it to keep this reaction going. We call that amount a critical mass. Now, critical mass is defined as the amount of fissionable material needed to sustain a chain reaction. Now, I said Miner, Hahn, and Stossman were Germans, and this took place in the 1930s. If you know anything about history, 1930s, Nazi Germany, not a good thing that they have this reaction potentially being at their use. So as a result of that, I forgot. I got to go back a little bit. The process we're looking at, I forgot the actual reaction. We take a neutron and we're going to hit a uranium atom. That's going to be uranium-238 or 235. 238s we use in nuclear reactors. 235s we use in nuclear bombs. When we do that, it stops and breaks that atom apart, forming krypton and barium, and it generates 3 to 4 additional neutrons. They go strike at 3 or 4 different atoms and continue the process from there. Now, as I was saying, the Nazis, the Germans, were beginning to get this process done. So this guy gets nervous. And his name, of course, you should recognize him. That's Albert Einstein. Albert Einstein wanted to do something. He had a friend of his named Leo Szilard. Szilard and Einstein were both nationalized Americans from Germany. They were both Jewish, and they knew the problems with the Nazis. So Einstein wrote a letter, August 2nd, 1939, to then President, again, it's his name, FDR, Franklin Delano Roosevelt. Now, Roosevelt identified this was a potential issue, so he started right away a process called the Fission Project. Now, the Fission Project really didn't go anywhere because there wasn't a lot of support for it. It wasn't until 1942, specifically December 7th, 1941, that the whole ball game got going, because on December 7th, 1941, Pearl Harbor happened. A week later, we declared war on Japan. Germany declared war on us. We were in World War II, and the Manhattan Project was born. Manhattan Project is where nuclear fission got its origins. Now, when it came time to the Nuclear Fission Project, there were 4 main sites. The first site was Los Alamos, New Mexico. Now, Los Alamos, New Mexico is an extremely isolated spot. It's a 4-day bus drive to anywhere. And there's 2 main reasons why they did that. First of all, safety. This was a very, very dangerous experiment. They want to make sure they didn't hurt people if they didn't have to. When they did the original research on it, they calculated there was about a 4 to 5% chance of complete atmospheric inversion. In other words, the atmosphere would inverse, we lose our ozone layer, life will be over. Only 4 or 5%, but hey, they were pretty confident. So there was a kind of safety they were concerned with. Second reason is secrecy. This is a top level secret weapon. They didn't want anybody to find out about it, so keeping it as far away from anybody else was a good thing. Second site they had was in Oak Ridge, Tennessee. In Oak Ridge, Tennessee, it was the dam site there where they produce uranium-235. They used a centrifuge to spin up the uranium and lift the lighter 235 from the heavier 238. 235, uranium has more energy, so that's what we did. So to get enough fissionable material, they had enough for 2 bombs with uranium. Third place they worked was in Richland, Washington. Richland, Washington, where they made plutonium. With the plutonium, they had enough for 1 bomb. So enough for a total of 3 bombs. Now, The problem with this is in order to cause the plutonium, a synthetic substance, to come together, they literally slam two elements together using a major magnet. The first time they turned that on, the magnet was so strong it literally ripped the building apart. So that took some work. And the last site was in Manhattan, Washington. This was just centrifuge things, basic paperwork going on there. It really messed the enemy up. We caught Japanese subs in New York Harbor. We caught a couple of Nazi spy groups in Manhattan trying to find it. It wasn't there, but it was a good trick to keep them away. Now, there were 3 bombs that were generated. 2 of them were dropped. The first one that was tested was called Trinity. Trinity looked like a little boy. No, it was like the Fat Man. But what we have here in this little boy is we have hollowed out uranium. So we have a piece of uranium-235 borrowed out so that little end here can be blown into it. When it blows into it, there's 2 metals here, lithium and polonium. Lithium and polonium, when slammed together, generate neutrons. Neutrons go into the uranium. Uranium nuclear fission, and whammo, bammo, explodes. Now, the way this explodes is with an altimeter. We want it to go off in the air. We don't want it to go on the ground. So at a given altitude, it would detonate, cause explosion, the slam them together, cause a nuclear fission, and get the reaction. Little boy, bullet bomb. This is the first type of reaction. The second type was called the Fat Man. Now, the Fat Man is compression bombs. In the middle here, we have our plutonium, and we're going to put dynamite all the way around it so that pushes in at the same exact time. When it does that, it causes a fissure, a break, and then release the energy, okay? And then we did have a third bomb, Trinity, which we detonated in Los Alamos. We tried to make a fourth bomb called the Thin Man, but we didn't have enough uranium to do that. So what's going on here? It is now August 6, 1945. We have the bomb. We've tested it. Oppenheimer has made his famous quote, "I have become death, the destroyer of worlds." This man here, Harry S. Truman, now just so you know, there's no period there because Truman's middle name is S, not abbreviation. It's just S. He's now president of the United States. Roosevelt had been president of the United States, had served 3 terms, probably going to go for 4, but he dropped dead at the Resolute desk in the Oval Office. And so Truman was immediately read in on the Manhattan Project. He had known nothing about it before because Manhattan Project was a need-to-know operation, and Harry need to know. So as a result, he's given the information. Now, at the time, there were 3 people we were battling in Germany, Italy, and Japan. Italians, they're out a long time ago because Italians are lovers, not fighters. The Germans, well, Germany made a huge mistake by attacking Russia. And when they do, the Russians push back. And so Germany ended up with a 2-front war. When they did, they eventually collapsed. Hitler took a lead sandwich with his new bride, otherwise known as he killed himself in the bunker. Germany's out. So we're left with Japan. Well, we could have waited and let Russia go all the way back across their country. It would have taken about 6 months to a year to move all the resources to the Eastern Front. So Japan would be in a 2-front war. But there was a definite problem with trying to battle Japan this way. Japan had something called the Honor Code, which means they would die before they would give up. A couple examples of that, kamikazes and Kitons. Now, you probably know about the kamikazes. Those are the guys that flew the planes into ships, blew them up really bad. The Kitons were submen. They did the same kind of thing except with torpedoes. See, in 1945, they didn't have heat-seeking or sonar technology, so the only way to get a bomb to an item is to get it there. If you were a good ship captain, moved your ship out of the way, the torpedo would miss, have no effect. So what the Japanese did, because of the honor code, they didn't want to lose, they put a man on top of the torpedo and they drove it into the side. Quite honor code. Another example of that was the Philippines. In the 1940s, a group of Japanese soldiers had got disconnected from mainland Japan. And they fought for another 30 years, guerrilla tactics, until their officer gave them the stand-down command. They saw planes going over their heads for Korea and the Philippines. They were convinced the World War was still going on, and they kept fighting. It didn't matter that they were getting close to their 70s in age. They still fought on because the honor code, death before dishonor. And it was estimated that if we tried to go island to island, the Battle of Iwo Jima was horrible, totally destructive, killed many people. It was estimated that 100,000 American soldiers would have been killed if we tried to go battle to battle that way. So, August 6, 1945, the Enola Gay drops their first bomb on Hiroshima. Total devastation. Japanese didn't give up. So about 2 weeks later, we drop the Fat Man on Nagasaki using the airship, the Flying Fortress, the boxcar. Now, after that, Japan surrendered. Why? Because they thought we had a bunch. We only had 3. We'd blown them all up. We were all done, but they didn't know that. So as a result, that is how nuclear fission came into be, and that's how nuclear energy became aware to the rest of the world. Now, is there a good use of nuclear fission? Yes, nuclear power. There are 3 main benefits of nuclear power. First of all, it's very efficient. I had a nuclear engineer speak to my class one time. A rod about that long and that thick, so very small rod, will run every system on a nuclear attack sub for 6 months. Very, very efficient. Low amount, a whole lot of energy, very efficient. Second, it's clean. You see this reaction up here? That smoke, that's just water. We're not producing any chemicals here. We're not producing any toxins in the environment. And third, it's abundant. We believe we have enough nuclear fissionable material to last probably 500 to 600 years. So it's a very abundant energy source. Now, this is a nuclear reactor. That seems really complicated, so I'm going to make it a lot simpler. I had a group of students do a science test, and so they drew this diagram that I showed them on their test, and they got points, so it's got to have some blessing. All right, so here we do. Draw this out for yourself. What do we have here? On the outside of this, there's concrete. We have concrete all around that to keep the radiation inside. Inside of there are 3 to 4 little containers of uranium-238. We're going to use 238, not 235, to cause a reaction to take place. Now, we have all of them 238. We're going to put control rods in there. Control rods in the United States are made of cadmium. What they do is they absorb neutrons, slow the reaction down. So if I slowly put them in, I'll absorb the neutrons, slow the reaction, keep it under control. Pull it out, reaction goes faster. Now, the water inside of there is called heavy water, H3O, and we're going to pump that hot water around, and that's hot water is going to buy cold water. When hot water goes by cold water, it's going to generate steam. Steam is going to turn a turbine. Turbine is going to produce electricity. So that's how nuclear power works in a nutshell. All right, now, one of the problems with nuclear power we always think about is disasters. There have been 3 major disasters. In reality of energy power plants, 3 is nothing. Coal has had a lot more than that. But because nuclear is so excessive, there's a concern with it. So let's start with the first disaster. TMI, 3 Mile Island, Pennsylvania. It's about 7 hours from where I'm at. What happened at 3 Mile Island is those 2 pipes, there was a crack inside of there. Nuclear steam was vented, and that was a concern. Now, the really bad one took place in Chernobyl, Ukraine, in this old Soviet Union. What happened here on April 28, 1986, I'm a freshman in college, I remember this, they were running a reactor at 120% efficiency. Now, there's a whole lot of story about why they didn't have enough resource and had to do with the Star Wars program. So if we get together, I'll talk to you a little bit more about that. But they didn't have the cadmium like we do. They had graphite, and the reactor got too hot. They slammed the rods down. The rods detonated because graphite carbon explodes, and the reactor melted down. Really bad. And then they eventually had to dig underneath it and fill it up with supercoolants. The last one that took place, Fukushima Daiichi, Japan, on March 11th, 2011. What happened there was an earthquake. Now, the earthquake slammed the reactor, causing it to go into a meltdown phase. They were starting to shut it down, but before they can completely shut it down, a tidal wave, a tsunami came in, flooded the generators, shut them down, and now the reactor is going out of control. The only way to stop it is they literally had to pump seawater directly into the reactor and pump it out. Not a good thing. Now, all of these things, these disasters are terrible, but that's not the biggest problem with nuclear power. Nuclear power problem is waste. So what would you do with waste? You basically take it, put it on a slab, put it in a concrete building, put it underground, and you sit it there forever. So that is the only way to do nuclear waste, to contain it, to store it forever, and never let it get out. All right, so there's another process they're hoping will be more efficient. That's called nuclear fusion. That's energy from the combining of atoms. That's what takes place in a sun. So here we have an example. We have tritium, which is H3, with deuterium, H2. In the reaction, the other side of the reaction looks like this. And when we do that, we're going to generate helium and a neutron, and additionally, we're going to generate a great deal of energy. So tritium to deuterium, producing helium and a neutron, that's one fusion reaction. And hydrogen plus lithium to form two helium atoms, that's a second fusion reaction. Now, the major way that we use fusion today is in a bomb. How do we do that? How do we set that up? I don't know. We're not allowed to explain that. Are they working on nuclear fusion reactors? Well, the only one that works efficiently is the sun. There are ones that we theorize that can work. When the main one we think might work would be like this. This is called star in the bottle. We take 4 lasers. Okay, and a laser is an acronym. It means light amplified by simultaneous emissions of radiation. We take seawater, fire lasers together, compresses in, and we generate a microstar. From that microstar, we're able to get energy. Now, the problem is it puts a great deal of force on the lasers, and the lasers crack. If we can get a laser crystal that can absorb that kind of pressure and keep going, we might be able to make nuclear fusion more efficient and much more energetic. All right, that's it for nuclear fusion and fission. Hopefully that wasn't too bad. Take care. God bless.